Welcome back. We're going to talk about the alkylide reduction reactions that will lead us to prepare secondary alcohols. Now, the only way to really make this happen, since we're going to introduce one extra carbon to the mix, is to start with the aldehydes, because the aldehydes only contain one carbon bound to that carbonyl, and the second carbon that we're going to add to it is what's going to yield the secondary alcohol. All right, so let's take a look at the process. So let's say we have a lithium alkyl, so propyl lithium. If we react propyl lithium with the following aldehyde, then technically the sequence is as follows. The carbanion, which is your alkylide, will attack the carbonyl carbon as shown right here. And then those bonds of the carbonyl will have to go back to the oxygen to form a lithium alkoxide. Now notice that that entire propyl group has been added to what used to be the carbonyl carbon, right? You still have the hydrogen, by the way. The hydrogen that was drawn out here is still present in the bond line formula, right? We're not drawing it because it's the bond line formula, but it is there. Now, once you form the lithium alkoxide, then all you have to do is quench the reaction by adding water. The lithium alkoxide will react with water, removing a proton and producing lithium hydroxide in the process. And of course, now we have our alcohol. You could also do this with a Grignard reagent. So this is not exclusive to the lithium alkyls. This can absolutely be done with the Grignard reagents. And in some ways, you rather do this reaction with Grignard reagents because they're a little bit milder. They still accomplish the same job, but they are a little less likely to undergo side reactions. There is a chance that your lithium alkyl may start doing other chemistry that you don't want it to do because this is so basic and the lithium doesn't really provide much of a stabilization to the carbanion that it could start like deprotonating other things like your alkenes and then forming byproducts. So those are things that could happen, but the Grignard doesn't have those problems. And typically when we chemists want to do this type of reactions, turn your aldehyde to a secondary alcohol, the Grignard reagent is usually the thing we go for. Okay, so here we're adding an ethyl group, right? So this is ethyl Grignard. So the ethyl group attacks the carbonyl bond is broken with electrons being provided back to the oxygen, yielding your alkoxy magnesium chloride complex in this case. And then finally we add water, which will quench the reaction because the alkoxide will attack the water, remove a proton, you end up kicking away hydroxide, and at the end you end up producing magnesium chloride and magnesium hydroxide, half and half of each. And let's not forget, this also will produce your secondary alcohol. Okay, so that's basically the mechanism for this reaction. There's really not a lot to it. But this brings us to the tertiary alcohols. In fact, there's a number of ways that we're going to be able to form tertiary alcohols with the various alkyl reagents that we've talked about so far. So we're going to start with this, the ester or acyl chloride for the matter, and we're going to see how we can make tertiary alcohols out of it. Now this is a very similar situation to what we've seen with the aluminum hydride reagents. I'll show you a little bit later how we can stop at the ketone stage starting from the ester or acyl chloride. But right now the Grignard reagents are going to take us directly from either ester or acyl chloride all the way to the tertiary alcohol. Okay, so first things first, I'm going to show you, how it works for the ketones, right? So if you start with a ketone automatically, okay, well, that's what you have, right? That's your reagent. And if you react it with a lithium alkyl, the lithium alkyl will be added to that carbonyl carbon. The CO double bond will be broken. A set of those two electrons will be pushed back to the oxygen to give you a lithium alkoxide. Notice that the isopropyl group is now added to what used to be the carbonyl carbon. Oh, and by the way, this carbon right here is chiral because we have 4 different groups. But because the reagent right here is trigonal planar, the alkyl can attack from the front or the back of the molecule. So technically speaking, what you're forming right here is nothing more than a racemic mixture of the alkoxide. And once you protonate it, of course, you don't change that fact. The alcohol that you generate at the end is also going to be racemic. Like we saw before with the secondary alcohols, if you do treat a ketone with a Grignard reagent, you can enact the same type of transformation. Your ethyl group can attack the carbonyl carbon of the ketone, producing an alkoxy group that's now interacting with magnesium, and then that can be quenched with water to give you the alcohol. You also produce half an equivalent of magnesium chloride and half an equivalent of magnesium hydroxide. Now, like before, I would say that for this type of reaction, probably the Grignard reagent is the preferred route to take over the lithium alkyl, because lithium alkyls are a lot stronger bases, a lot more reactive, and other side reactions can take place that may not be exactly what you want it to happen. Like you might end up deprotonating the aromatic protons instead of attacking the carbonyl carbon, something that is not necessarily seen or really ever seen with the Grignards. Okay, so that's if you start with the ketone already. But what if you have the ester or the acyl chloride? What this is telling us is that we're gonna have to produce the ketone midway through the reaction, but that ketone, as we saw already in the previous slide, is gonna react with further Grignard or further lithium alkyl. So let's see how this happens. In fact, you will come to recognize that this mechanism is no different than the mechanism of hydride reduction. In essence, we're going to do the same thing. So here I have phenyl lithium being treated by the following ester. So phenyl lithium will attack the carbonyl carbon. Those two sets of electrons will be pushed back to the oxygen, giving you a lithium alkoxide. And now we have this situation that you may recall already of having two carbon-oxygen single bonds. One of them is actually a full alkoxide. The other one is an alkoxy group with carbon bound to it. And normally this will be a terrible leaving group, but because of the same premises that we've talked about in the aluminum hydride discussion and the pre-arrangement of the molecules, the alkoxy group actually serves as a leaving group. So you end up reforming the carbonyl carbon. So this bond comes back here to form that CO double bond. At the same time, the alkoxy group needs to get out of the way. And once the lithium alkoxide is removed, you now form the ketone, which is the midway step in the sequence. Since we're treating this with lithium, with phenyl lithium, that's reactive enough not just to react with the ester, but also with the ketone. So the moment the ketone is formed, it's already being reacted with phenyl lithium, right? So that attacks the carbonyl carbon, the electrons get away towards the oxygen, you now form your lithium alkyl. But what I want you to notice right here is that the initial molecule didn't have any phenyl present. By the time we finish the second alkylation, we now have two phenyl groups present. That's because we are reacting the ester with two equivalents of lithium alkyl. And so this is a nice way of introducing two groups of the same kind onto that very same carbon, right? The carbon that used to be the carbonyl carbon, the carbon that still bears the oxygen. And the final stage is still the same. You gotta add water to quench the reaction and produce your alcohol. Okay, now once more, but this time with a Grignard. Okay, so here we have cyclohexyl Grignard that we're treating with ethyl acetate. All right, so we react these two molecules. The Grignard attacks the carbonyl carbon. The double bond is broken. Electrons go towards the oxygen to give you that magnesium alkoxy derivative, but you still have that ethoxy group bound to it, right? So this once more serves to reform the carbonyl double bond and kick away the ethoxy group. So this time we're going to be producing half an equivalent of magnesium chloride and half an equivalent of magnesium ethoxide while producing the ketone, right? So we still have the cyclohexyl that we just added, we still have the methyl that we just added. So you can see those two groups present in the ketone. Now the ketone is susceptible to reaction with a second equivalent of Grignard, and that's literally what's going to happen here. We have the cyclohexyl attacking the carbonyl carbon. That pi bond is broken, forming your new alkoxy magnesium bond, ionic bond, mind you. And then notice once more, we started with the Grignard with cyclohexyl. We have added 2 cyclohexyls by the end of the reaction with the ester. And so treating this with water is now going to yield one equivalent of that alcohol. All right, so the same idea than with the lithium alkyls, but I would say that the particular reaction with esters is best to be carried out with magnesium, Grignard reagents, as opposed to the lithium alkyls, because the lithium alkyls are almost guaranteed to carry over a different reaction, a reaction you're not going to learn about in the first semester organic chemistry class, but it's a reaction you'll learn about in the second semester class. So for sure, you do not want to use the lithium alkyls with esters, even though I presented the mechanism with them. Grignards are going to be the better way to do this. Okay, so that brings me finally to ketones. In particular, how do we make ketones if we start with esters or acyl chlorides? Now, in particular, esters are really not going to be an option for us, but the acyl chloride can actually be utilized to form ketones. And this is where the lithium cuprates come into play. Because even though lithium alkyls, like the ones shown right here, so this is butyl lithium, are very reactive, very strong bases, and not super selective, by adding copper, what you're basically doing is substituting that interaction of lithium carbanion with an actual carbon-copper bonding interaction. And you can consider this a coordinated covalent bond, but it's a much stronger bond than your lithium alkyl, right? Which by all intents and purposes is regarded as being mostly ionic. This has got a little bit more covalent character, and because of that extra stability, and right here I'm showing you the electronegativity differences between carbon and lithium versus copper and carbon. And so you can see that the electronegativity difference is not so great in this bond versus over here. That's definitely ionic, like there is no even a question. A 1.57 electronegativity difference is very much an ionic contribution. This is almost on par, on the other hand, for the cuprates, with a polar bond, a covalent polar bond. So this is a little bit more mild. It's not going to go after every single group. And this is the reason why we're going to be able to use it to stop midway. All right, so as you can see here, yes, we have the greater ionic contribution for the lithium alkyl, a greater covalent contribution for the cuprate alkyl bond. So this makes that a milder reagent. And specifically, the way in which we use it is we take that acyl chloride and we react it with the lithium cuprate. And automatically, we get only one carbon to attack that. And once more, remember that your acyl chlorides can form that linear shape via that equilibrium. So you have a lot more accessibility to this carbonyl carbon than you might think. So you can add that carbon, that extra R group, to produce your ketone. And the moment you do that, you can no longer form that linear shape. The carbonyl carbon is not as accessible as it was before, and that's what kind of makes this stall at the ketone stage. Only with lithium cuprates, however. Okay, so a way to look at this would be to say, okay, we have the following acyl chloride compound. We're reacting it with ethyl cuprate, lithium diethyl cuprate. And so the ethyl attacks the carbonyl. You break the CO double bond to form the following intermediate. And here you do have a pretty good leaving group. So the double bond can form almost right away while kicking the chloride out. And this forms your final ketone. Now, one more thing that I'll tell you in regards to the cuprates, which is kind of interesting, is that you can actually form carbon-carbon bonds between alkyl halides and the lithium cuprate. And the reason why this is important is because you could actually do it not for every single reagent ever that you could encounter, but you could, for a select few, you could actually introduce this alkyl reagent and substitute it for the halogen, kind of like an Sn2 reaction. But the difference is that now you could have a secondary alkyl halide that, by all accounts, with a really strong base like the alkylides, this should be definitely an elimination reaction. Like, I wouldn't even question it. And if it was a lithium alkyl, for sure this would be an elimination reaction. But because we're using lithium cuprate, which is a much milder reagent, this can actually carry the Sn2 reaction without much of a problem. So that's one of the key features that I, kind of want to highlight. That it's important, right? This cannot be done. Like, if you wanted to put an extra ethyl group right here, you could not do this with lithium alkyl or even the Grignard, the ethyl Grignard reagent. But the lithium cuprate will allow you to do the Sn2 reaction and yield the proper molecule without the problem of undergoing elimination site reactions. Okay. So last thing to be shown right here is that for the alkylide reagents, there is maybe a table that we can talk about. We could have the lithium alkyls or the Grignards, and if we react the aldehyde with those guys, we end up forming secondary alcohols. If we react a ketone with lithium alkyl or Grignard, we get tertiary alcohols. Carboxylic acids are a no-go, so we won't do reactions with them unless all you're trying to do is produce the carboxylate. Esters will form tertiary alcohols, the same as acyl chlorides. But if you use lithium cuprate, you can use the acyl chloride to form a ketone. Okay, so that basically summarizes this entire lecture. I hope you enjoyed it. And this basically concludes the entire set of reduction and oxidation reactions. In future lectures, we'll probably examine synthesis in general. But I hope you found this helpful, and I will see you in the next video. Bye-bye.